In this example problem, we're going to use the force-in-the-tendon approach to calculate stresses and deflections for the given section. We'll first calculate our pre-stress losses using our PCI Design Handbook approach. Then we'll check stresses at midspan and at the end of the beam using our gross sections, or gross section properties. And then finally, we'll use our gross section properties and the PCI Multiplier method to check our midspan deflections. We're going to look at a standard double T section, a 12 DT30 with a 30-inch depth. We are given some information on our loading, information on our concrete strength, the release strength and ultimate strength of the concrete, the stress in the strand before transfer, the span length, and the relative humidity. For standard precast sections, we'll often be given our gross section properties. So the standard sections for this 12 DT30, I obtained from the PCI Design Handbook, and I give them to you right here. In terms of strand area and eccentricity and material properties, we're going to assume we already designed the beam to have 18 half-inch diameter strands with a height of 10 inches from the bottom. And they're going to be straight strands along the length of the beam. We have other information on our strands given here. We can calculate the release modulus and the modulus using the ultimate concrete strength, just using our ACI 318 equations shown here. The first part of the problem asks us to find our pre-stress losses using the PCI Design Handbook approach. And we'll start by finding our elastic shortening loss. To do this, we need to find the force in the strand before transfer, so this P sub j, and we'll do that by taking our F PBT times the area of our pre-stressing. So we'll get a total force as shown there. The next step is to find our self-weight moment. So we'll just use our WL squared over 8 equation and change our units to kip inches. So we do that there. And then we can plug in all of our known values with our gross section properties to find the stress in the concrete at the same level as our pre-stressing. So we'll have 0.9 times 555 or 557.7 kips divided by our gross area 928 inches squared plus 557.7 times our eccentricity squared, so 12.94 inches squared, divided by our moment of inertia here, which is 59, or gross moment of inertia, 59,997 inches to the fourth. Close our bracket, subtract off moment, our self-weight moment, 3,645 kip inches times 12.94, our eccentricity, all divided by our gross moment of inertia, again, 59,997 inches to the fourth. So this will give us a stress at the centroid of our pre-stressing strands equal to 1.155 KSI. We can take this stress times the ratio of our modulus for our pre-stressing, 28,000, divided by our modulus of our concrete at release, 3,372, times the stress, 1.155, which will give us an elastic shortening loss here of 9.8 KSI. We can use that elastic shortening loss so we can to find the stress in our strand after transfer. So our stress before transfer minus elastic shortening loss gives us our stress after transfer. And then we can take that stress times our concrete area to give us the force in our pre-stressing strands after transfer. And we'll use this pre-stressing force with our gross section approach to find our stresses in the section at release. Next, we can find our pre-stress loss due to creep. And to do this, we first need to calculate the moment due to all of our superimposed dead loads. So we have our moment there equal to 450 kip inches. So then the stress at the centroid of our pre-stressing strands due to our superimposed dead loads is going to be equal to that 450 kip inches times our strand eccentricity, which is 12.94, divided by our gross moment of inertia, which is 59,997 inches to the fourth, which will give us a stress equal to 0.097 KSI. We can use this stress with the stress that we found on the previous slide to find our creep loss here. So we have 2.0 times the ratio of our pre-stressing modulus, 28,500, divided by the modulus of elasticity for our concrete using the ultimate strength of our concrete, 4,031 KSI, and then times the stress we found, F sub CIR, which we found on the previous slide, 1.155 KSI, minus 0.097 KSI, which will give us a value here of 15.0 KSI, which is our creep loss. Next, we can find our loss due to shrinkage. To do this, we'll need our volume to surface area ratio and relative humidity. The volume to surface area ratio was given for the section, and that's a given property in the PCI Design Handbook. And the relative humidity we would determine based on the location of our structure. So that was given in this project as 70% as well. The K shrinkage for pre-tension components is going to be equal to 1. But using our volume to surface area ratio and relative humidity, we can calculate our shrinkage strain. So here we have 8.2 times 10 to the negative 6 times 1.0 times 1 minus 0.06 times 2.3 inches. Sorry, I need to close that parenthesis. And then 100 minus 70. And we'll get a shrinkage strain here equal to 0.212 times 10 to the negative third. We can take this shrinkage strain, 0.212 times 10 to the negative third, times the modulus for our pre-stressing strands, 28,500 KSI, to give us our total shrinkage loss of 6.0 KSI. So there's our shrinkage loss and our creep loss. Next, we can find our pre-stress loss due to the relaxation of our pre-stressing strands. We'll use the PCI Design Handbook approach, and to do that, we need to use some of the tables that are provided on this slide. First, we know that we have grade 270 low relaxation strands, which we will typically have in practice. So we come here to this table, and we can find our K relaxation equal to 5,000 PSI or 5 KSI, and our J equal to 0.04. Looking at our ratio of our jacking stress to the ultimate stress of the strand, we can find that ratio is equal to 0.75. So in our C table, we'll come here to 0.75, and we know we have low relaxation strands. So we'll be in this column here. So you can see we'll have a C value equal to 1. So that's where we get our C equal to 1. Plugging in our K relaxation, our J, and our C values with our shrinkage strain, creep, or shrinkage loss, creep loss, and elastic shortening loss, we can calculate our relaxation loss to be 3.8 KSI. We can add together our shrinkage loss, our creep loss, and our relaxation loss together to get our long-term pre-stress losses. And then we can add that long-term pre-stress loss to our elastic shortening loss to get our total loss, total pre-stress loss. We can then take the stress in the strand before transfer minus our total loss to get the strand stress after all losses, and take that times the area of our pre-stressing to get the final force in the pre-stressing, P sub F. And we'll use this pre-stressing force when finding our stresses due to our sustained loads and also our stresses due to our service loads. We're now ready to calculate our stresses using our gross sections at midspan and at the end at release due to our sustained loads and due to our service loads. So we'll start looking at our stresses at release at midspan. If we're looking at release, we want the pre-stress force immediately after transfer, so P sub I, and we'll use, or we'll only include our self-weight moment, M sub self-weight. So plugging in these values with our gross section properties, we can find the stress in our top and bottom fiber. So our F sub CT is equal to negative 530.8 kips divided by our gross area 928 inches squared, plus, so our strand eccentricity is going to cause tension in the top. So we have 530.8 kips times 12.94 inches times the distance between the centroid and the top of the section, 7.1 inches, divided by our gross moment of inertia, 59,997 inches to the fourth, minus our self-weight moment is going to add compression in the top, so we'll have a minus sign here, minus our 3,645 kip inches times 7.1 divided by 59,997 inches to the fourth will give us a top fiber stress here of negative 0.193 KSI. We can compare that to our compression limit here, 2.1 KSI, and see that our stress checks. Next, we can check the bottom fiber stress at release at midspan. So here our FCB is going to be negative 530.8 kips divided by 928 inches squared minus 530.8 times 12.94 times the distance between the centroid and the bottom of the section, so 22.9 inches, divided by our gross moment of inertia, 59,997 inches to the fourth. And then plus, we're adding tension with our self-weight moment, 3,645 kip inches times 22.9 divided by 59,997 inches to the fourth. So we'll get a bottom fiber stress here equal to negative 1.804 KSI. So we can see this is, again, less than our compression limit, so we're okay here as well. Next, we can check our stresses at release at the ends of our beam. We're going to assume in this problem that we're right at the ends of the beam, so we have no moments. You would actually want to check your stresses at your transfer length, but if your stresses check at the end of the beam, typically they'll also check at the transfer length. So here we'll have the same first two components as we did on the previous slides, except we have no flexural stresses from our moments. So adding those together, we can get the top fiber stress of 0.236 KSI in tension. We can compare this to the tensile stress limit at release in the end regions, and we can see that our stresses check here. We can do the same thing in compression here, or sorry, at the bottom fiber. So adding together all of our components except no stress from our moments, and we'll get a compression stress of about 3.2 KSI. We can compare this to our compressive stress limit and see that we're actually over our compression stress limit. So this is no good. Because of this, we would need to change something about our design. So we would need to either debond some strands, increase our concrete strength at release, or we can also go and check our stresses at the transfer length. If we check at transfer length, this will bring down our compressive stress a little bit. We can now check our stresses due to all of our sustained loads at midspan. When we're looking at our sustained loads, we need to use the stress in our pre-stressing strands after all of our pre-stress losses, so our P sub F. So we find that force there. We're also going to include into this calculation the stresses that are caused by all of our superimposed dead loads. So we need that additional moment here when we're looking at midspan. So adding all of our components together, we'll get our F sub CT to be equal to 462.5 kips divided by our gross area, or sorry, negative here. So gross area 928 inches squared plus 462.5 times our strand eccentricity 12.94 times the distance between the centroid and the top of the section, 7.1 inch, divided by our gross moment of inertia, 59,997 inches to the fourth, and then minus, because we have the same gross moment of inertia and the same distance between the centroid and the top of our gross section, I'm going to combine our moments. So we have our self-weight moment, 3,645 kip inches plus 450 kip inches times 7.1 inch divided by 59,997 inches to the fourth. And we'll get a stress here equal to negative 0.276 KSI. So we can compare that to our limit, our compression limit due to all of our sustained loads, and we can see that we're less than the limit, so we check here. We can do the same thing for our bottom fiber stresses. So we'll have negative 462.5 kips divided by 928 inches squared minus 462.5 times our strand eccentricity, 12.94, times the distance between the centroid and the bottom of the section, 22.9 inches. And then all this divided by 59,997 inches to the fourth. And then again, I'm going to combine all of our moments. So 3,645 kip inches plus 450 times 22.9 divided by 59,997 inches to the fourth will give us a stress here in the bottom fiber equal to negative 1.220 KSI. So here we can compare this stress to this compression stress to our limit, and we can see that we're okay here as well. Next, we can check all of our stresses due to our sustained loads at the ends of the beam. We'll use the same force that we did before, and we'll have the same two first components that we had before. But again, because we're assuming that we're checking at the ends of the beam, we're going to assume that we don't have any stresses from our moments. If we check here, we'll check also at the transfer length. If we don't check here, then checking stresses at the transfer length will help us. So here we can check our top fiber stress and see that we actually have a tensile stress at the top. We don't have any tensile stress limits under sustained loads, so we're okay here. And then checking the bottom fiber, we can see that we have a compressive stress equal to negative 2.786 KSI. And comparing this to our compression stress limit due to sustained loads, we can see we're above this limit. So again, we're no good here. So we can check the stresses at the transfer length and see if that helps us. If it doesn't, we would need to increase our concrete strength or modify our strand locations, or possibly debond our strands in the end region. Next, we can check all of our stresses due to service loads at midspan and at the end sections. This will be the same calculations that we had before. We're just adding in a stress component from our live load moment. So we're just adding in another component here. So adding in that in the top and adding in that in the bottom. And you can see at the top, we now have a compression stress of negative 0.647, which is below our compression stress limit. So we're okay here. And at our bottom fiber, we now have, we still have a compression stress, but it's right around 0. So we check against our compression stress limit. Note that typically we will be close to the tensile stress limit. So this is the tensile stress limit, 7.5 times the square root of F prime C. So because we still have a lot of room between the bottom fiber stress here and the tensile stress limit, we could try in our design taking out some of our pre-stressing strands. And if we take out some pre-stressing strands, that'll help us with some of the problems we were having on the previous slides. And it'll also make our section a little more efficient. So it'll bring this value closer to the tensile stress limit. Finally, we can calculate all of our stresses due to our service loads at the ends of the beam. And again, we'll assume we're right at the end. So we're assuming that we have no moment. So we have no stresses from our moment. These two components are the same from before. So we have a tensile stress at the top, a compression stress here at the bottom, but we are below the tensile stress limit and below our compression stress limit here. So we're okay with this check. The final part of this problem is to determine the deflections using the PCI Multiplier approach. And the first step that we'll do in this approach is we want to calculate all of our base deflections, which I'm highlighting in blue in this table. And the first base deflection that we'll find is our deflection due to pre-stressing. If we have straight strands, we can use the equation that's shown here, where our deflection is going to be equal to negative because it's going to be an upward deflection. Our eccentricity, 12.94, times the strand stress immediately after release. So, strand force in the strand immediately after release. So taking our elastic shortening losses off, which will be 530.8 kips times 50 feet times 12 inches per foot squared, all divided by 8 times our modulus at release, 3,372 KSI, times 59,997 inches to the fourth. So this will give us a deflection here of negative 1.528 inches. We also need to find our deflection due to self-weight, superimposed dead load, and live load. So our deflection due to self-weight is going to be equal to 5 times our self-weight distributed load, which will be 0.972 kips per foot, times 1 foot per 12 inches, times our length, 50 feet times 12 inches per foot to the fourth, divided by 384 times the modulus at release, 3,372 KSI, times our gross moment of inertia, 59,997. 997 inches to the fourth. So that'll give us a self-weight deflection of 0.676 inches, and this is downward. We can do the same thing with our superimposed dead load. Note though, with our superimposed dead load, we want to use the modulus of elasticity of our concrete considering the ultimate strength of the concrete. And we can see a downward deflection of 0.07 inches there, and then a downward deflection due to our live load of 0.44 or 488 inches, also using the modulus of elasticity considering the ultimate strength of our concrete. So now we have all of our base deflections, and we're ready to use the PCI multipliers. If we want to find the initial camber, all we do is add together the deflection from the pre-stressing to the deflection from our self-weight. So we can see an initial camber of negative 0.852. So this will be negative, so we have an upward deflection. Our final camber, we add in our PCI multipliers, so 2.45 and 2.7. 2.45 times our pre-stressing deflection and 2.7 times our self-weight deflection. And again, we can see an upward deflection here of negative 1.919 inches. So negative tells us it's upward. And to find our total service deflection, we can add in 3 times our superimposed dead load deflection and add in our live load deflection. So you can see our total service deflection here is negative 1.221 inches. There are several deflection limits in ACI 318. If we assume that we have a roof element with no attached elements likely to be damaged by excessive deflections, we need to make sure that the combination of our superimposed dead load and our live load is less than L over 240. So adding together these two components gives us about 0.7 inches compared to our limit of 2.5 inches, which means we would be okay here. So you can see through this example how we would check our stresses and how we would check our deflections. We found that some of our stresses didn't check, so we would need to modify our design, but we're not going to do that in this example. So that concludes this example problem.